Hi, welcome to another online lecture here for this is going to be on the first part of chapter 6. Today we're going to be taking a look at talking about light and kind of a bunch of the different properties or ways we often talk about or describe light. And then we're going to work on kind of relating a lot of those properties of light to atomic structure. Because it turns out light shares a lot of common properties with electrons in particular. In terms of like how we think about light, we can think about electrons in a very similar manner. And that actually gives rise to a lot of our modern kind of picture of atoms. And that's kind of what we'll work our way towards as the chapter moves along. But as a starting point, we're going to start out talking about light. So a little bit of kind of background, some definitions. When we talk about light in general, it's a form of something called electromagnetic radiation that we're actually able to see with our naked eye. And so that's probably the biggest thing about light is just the colors and things like that that we're able to see visually. That's what we refer to as light. Is the forms of electromagnetic radiation that we can actually see. Now, that term electromagnetic radiation, if you're not familiar with that, can define that kind of quickly here as well. Probably the easiest way that I like to usually think about it is that it's kind of a wave-like character form of energy. And so it's energy in nature, but it has a lot of wave-like properties associated with it. And so there's lots of different types of electromagnetic radiation. We'll look at a few of those here in a couple slides. Light is kind of a specific subset of electromagnetic radiation that we're able to visually see. And like I said, we'll get into some of those other types here in just a bit. Now, one of the reasons we care about light in particular, other than obviously it's what we can see, from a chemistry standpoint, visual light is very often of the right energy that it's able to be both absorbed and emitted by atoms. And so that's another reason why we're going to be talking about light a lot in this chapter and things we can kind of relate it to. We're going to talk about how exactly atoms are able to absorb or emit light, kind of what that process entails. And you'll see that a little bit in the lab for this week as well. And as I mentioned, not all electromagnetic radiation is going to be visible, only the small little bit that we refer to as light, and we'll get into kind of some specifics on that in just a second. But probably more important, we mentioned that there's this wave-like character to electromagnetic radiation, which means for the most part when we talk about light, we're often talking about its wave-like properties. And so when we characterize waves, the biggest things we're usually going to be talking about are going to be like wavelength and frequency. Those are probably the two most common ways that we talk about characterizing light, or kind of two of the more common properties they'll often describe about light. In general, we can also talk about amplitude if we're talking about waves, but it turns out the amplitude isn't going to have much meaning to us in terms of kind of physically, like any kind of like physical characteristics of the light, like as far as energy or things like that we're going to care about. Now, real quick, just to talk about kind of wavelength and frequency, give you kind of a clue of what these things are really talking about. We're talking about waves, so if you imagine almost like a sine wave kind of mathematical function, like if we talk about wavelength is going to be the distance between any two peaks in that particular wave that you're looking at. And then frequency is going to actually be based on, in a sense, how fast the wave is traveling. Frequency is going to be if you pick one particular point, you're going to monitor that point for some time interval and measure how many peaks of the wave pass that one point over that time interval. And usually the units you're going to see for frequency are going to be like per second, or so like 1/seconds for the units. You'll also see that unit described as hertz with the capital H lowercase z for the symbol or kind of shortcut for that unit. Hertz and inverse seconds are the same thing. So same units. So sometimes you'll see it written as like seconds to the -1 power. Sometimes you'll see the units for frequency written as hertz, but they're interchangeable. They do mean the same thing. And amplitude, if it mattered for much, would be the height of the wave. But like I said, this isn't going to come up very often for us. Our main focus is going to be on these two things, wavelength and frequency. And wavelength's important because when we talk about light, particularly colors and things that we can visually see, it turns out that every different color that we can visually perceive is a different wavelength of light. And so if we see something that has a purple color, its wavelength is usually somewhere down around about 400 nanometers. Things that are red in color, or even sometimes in what we call an infrared region of our electromagnetic spectrum, which I'll get to that again in a second. Things that are red in color usually are more like around 750, maybe up to around 800 nanometers for a wavelength. And pretty much all the other visible colors we can see are in between there. So this is kind of a general range of what our human eye is able to see as far as different wavelengths of energy. for different types of electromagnetic radiation. Outside of that range, most of us aren't going to really be able to see any colors associated with those wavelengths. So if we had a wavelength that's 1,000 nanometers, visually we aren't going to see it. Same thing if we had a wavelength that's 250 nanometers, we aren't going to be able to see that. But there are other ways for us to detect them. We just visually won't see anything color-wise for those particular wavelengths. Now, I do want to mention a couple things here. I mentioned before the electromagnetic spectrum, how there's different types of electromagnetic radiation. And we see here, this is kind of a chart with a bunch of different types of electromagnetic radiation, some of which you've probably heard at different points in time. And you notice that light is really only this little itty bitty tiny portion of this overall spectrum. And we see up at the top, these are the wavelengths of these different types of radiation. And at the bottom, we see these are the frequencies for those types of radiation. And so a few things here that I'm going to point out. One, if we compare the numbers for wavelengths and frequency, we notice they're kind of inversely related. Right? As the wavelengths get bigger and bigger and bigger, the frequencies get smaller and smaller and smaller, although they are still all very large. And that is normal when you're talking about frequencies for all of things that are going to be kind of showing up in this chapter. The frequencies are going to be usually very large numbers. Like the visible range of the spectrum in particular, like this little range, usually 10 to the positive 14th or 10 to the positive 15th hertz is going to be pretty common for those frequencies. Wavelength side of things, they're usually going to be pretty small, especially if we're in units of meters. They're usually going to be like 10 to the minus 7 for most of them for meters. And you see that down here. Although because of that, instead of talking about really small numbers, we'll often talk about things in nanometers, in which case things will usually be in the hundreds for the visible range, like we see here about 380 to 780. That's kind of the probably most commonly referenced range of what we refer to as the visible spectrum that you're probably likely to see. Now, some other things that we do see up here, like I said, you've probably seen most of these other types of electromagnetic radiation or heard of them at different points in time, right? We have radio waves and microwaves up here. These all have relatively short wavelengths. Relatively large wavelengths on this overall scale, and as a result have very small frequencies, even though the frequency numbers themselves are still quite large. And for like radio waves in particular, like you often look at like radio stations and you see things that are like, oh, it's 98.5 or whatever, like megahertz is the actual like kind of like unit that kind of goes with them. Well, mega, remember if you think about your SI prefixes from earlier this semester, mega is 10 to the positive 6th. It's like 98.5 megahertz. That'd be about something on the scale of like 10 to the 8th or 10 to the 9th hertz for frequency. And so your radio stations actually are the frequencies, like the real frequencies of those radio waves that the stations are being broadcast on. And so people probably have some familiarity with things like that. Microwaves have slightly higher frequencies, slightly smaller wavelengths, and those basically, the purpose of microwaves, obviously you use them to warm up food, but really what it does is it has the right kind of energy that it basically causes water to vibrate a lot and heat up very quickly. And that's kind of how your microwaves tend to cook things or heat things for the most part. You've probably heard of infrared region. So we have the infrared and the ultraviolet, which are basically on both sides of the visible spectrum. The infrared, again, slightly larger wavelength, slightly shorter or smaller frequency. Well, it makes sense. The infrared is close to the red end of the visible spectrum. Right? If we go past this 780, just to slightly longer wavelengths, we get into that infrared region. Whereas if we go just below 380, see to the left in this case, we get to the ultraviolet region. Well, 380 is where we see kind of the purple or violet colors in the visible range. So those are kind of our forms of electromagnetic radiation that are very close to what we can see, but visually we aren't going to be able to see things in those regions. But again, we have other devices or instruments that are capable of seeing those wavelengths, or at least detecting those wavelengths for us. So we can still use these for a lot of different practical applications. And if you go on and take a lot more chemistry in the future, you'll see like infrared spectroscopy and ultraviolet UV-vis spectroscopy are very common what's called characterization techniques to basically determine properties or characteristics of a lot of different molecules. The last couple ones over here, we see X-rays and gamma rays. So X-rays, again, people are probably pretty familiar with this as well. We see, again, shorter wavelength, higher frequency. Gamma rays all the way down here have the shortest wavelength and the highest frequency of all of these. And one last thing we'll kind of point out here, if you think about all of these different things in terms of like kind of almost a level of maybe kind of danger in a sense, of as far as like what things do we need to be concerned about being like exposed to, you usually don't hear too much about, oh, radio waves, microwaves, or infrared being dangerous. But like UV, X-rays, gamma rays. Like you hear people talk about like, oh, why it's damaging to stay out in the sun for too long, different things like that. These are the ones that are going to tend to be a little bit more dangerous. And we're actually going to see why here as we get through the next few slides. A lot of it has to do is as our frequency gets bigger and bigger and bigger, the energy of this electromagnetic radiation also gets bigger. And as a result, if the particles have a higher energy, then that can potentially cause more problems and potentially be dangerous at that point. So that's why you see people oftentimes concerned about things like UV, X-ray, or gamma rays. There's just more energy involved with those particular forms of electromagnetic radiation. All right, so equation-wise, some different things that we're going to see. We're going to talk about kind of relationships between wavelength and frequency. We saw in that previous slide that these things are inversely related, or in this case, I say like indirectly proportional. Basically, as one goes up, the other goes down. And so in terms of relating these two things together, it turns out there's actually a pretty easy equation that's going to relate wavelength and frequency. And that's going to be this equation that we see here. So we have this equation where C is equal to, this is the Greek letter lambda times the Greek letter nu. So the C in this equation is the speed of light, and this is a constant value. It's about 3.0 times 10 to the 8th meters per second. If you want to get to more significant digits, it's just less than 3. It's like 2.997, I think, or 2.998 times 10 to the 8th meters per second. Wavelength, so this lambda here in this equation, one thing that's important here, units, probably the most missed thing, kind of similar to the last chapter a little bit as well. One of the most missed things with these equations, because they aren't usually too complicated other than maybe the Rydberg equation, is just not using the proper units at the right time. So there will be a lot of switching from meters and nanometers and back and forth in this chapter. But if you're using this equation, since this speed of light has meters for its units, that means this wavelength also needs to be in meters for its units to use this equation. So do be careful of that when you go to use this equation. The Greek letter nu here kind of looks like an italic V. It stands for frequency, and again, our units here are either hertz or seconds to the -1, like inverse seconds. These are the same units. And basically, wavelength times frequency should always equal the speed of the light. And since this is a constant, if the wavelength goes up, frequency has to go down, and vice versa, like we saw in kind of that chart that was showing us those relationships in the last slide as well. And so this equation, I'll show a real quick example, just kind of using it. So here we have a question where we have a blue light given off by a mercury street lamp, has a frequency of 6.88 times 10 to the 14th hertz. What is the wavelength of this light in nanometers? So it's a pretty kind of standard type of question, kind of dealing with light as far as doing a calculation. So we saw the equation just a second ago, right? The C equals lambda times nu. If we're looking for the wavelength, that's the lambda part of this. So if we rearrange, again, divide the frequency over, the only thing we have to be really careful of as we put all of this in, the number we're getting out at the end of this, after we take our speed of light divided by the frequency, our units here are in meters currently, right? So we get 4.36 times 10 to the -7 meters. And most of the time, again, visible light, if it has a color, especially if there's a color associated here, it's talking about blue light, 10 to the -7 meters is going to be kind of the norm for anything that's in the visible range. It asks for our units in nanometers. So converting that to nanometers, kind of one additional step. Right, so 1 nanometer is 10 to the -9 meters, or if you wanted to write 10 to the +9 nanometers in 1 meter, that's also fine for your kind of your conversion step. But converting this, you should get 436 nanometers. And again, generally speaking, if it's got a visible color, it's probably going to be in that kind of 380 to 780 range of nanometers. Just to kind of have that kind of reference point is nice to kind of check a lot of your calculations as you're doing them. So wavelength of 436 nanometers should be our wavelength for this blue glow given off by these mercury street lamps. And that should make sense, right? We said 380 was the purple end of the spectrum, 436 is close to that, so purple is pretty close to blue in terms of kind of our general color spectrum, so it seems like a reasonable answer. All right, so everything we've looked at so far has really dealt with kind of talking about light as a wave and looking at kind of these just wave-like properties that when we talk about wavelength and frequency. But light's actually kind of stranger than that. It turns out light actually has some particle-like behavior as well, which is really weird to think of a wave, something being a wave and a particle at the same time. But we're going to see as we go through here a little bit more today that it's not all that unreasonable for that to happen. And in fact, that actually opens up some new ways for us to think about atoms as well. And so part of how we know light also behaves like a particle is through something called the photoelectric effect. And if you're not familiar with the photoelectric effect, this is actually what Albert Einstein won his Nobel Prize for. It was part of his work trying to help kind of explain and describe what was going on in this process. But it's a phenomenon that when you take light and shine it on a clean metal surface, it's possible for that light to cause electrons to be ejected from the surface of the metal. Now, the little image here that I've kind of included on this slide shows a couple different scenarios. So here we have a scenario where we have a very short wavelength of light, we shine on the metal surface, and these arrows represent the energy that the electrons getting knocked off the metal have when they get kicked off. So really short wavelength, we have a lot of energy in the electrons that get kicked off. As our wavelength gets longer, the electrons can still maybe get kicked off, but with less energy when they get knocked off the metal surface. And if the wavelength gets longer yet, then no electrons actually get knocked off at all. And then the other observation of this was if we shine just more total light to see what happens. So same wavelength as what we had previously when we injected electrons with a lot of energy. If we shine just more total light, we don't get more energy on the electrons, we just get more electrons knocked off. Again, shorten the wavelength a little bit, electrons all still getting knocked off, we're getting more of them than before, but same energy that for those electrons that they had previously when there was less total light being shined on the metal surface. And if the wavelength gets long enough, it doesn't matter how much light we shine, we still get nothing ejected. Now, what's important is kind of what this kind of means in terms of the energy involved with light and what's responsible for the energy of light. And it turns out really what this is kind of helping us figure out is that the energy of light is directly related to its frequency. That's this nu, right, that we saw kind of previously. So the energy of we're going to talk about photons in a second for light, is going to be equal to this constant h, this is called Planck's constant, times the frequency of that light. And how we kind of conclude this, if we're looking at these images here, it's the wavelength, which is, again, related to the frequency as well. As our wavelength got shorter, the electrons were getting knocked off with more force, or more energy. Well, if the wavelength is shorter, that means the frequency is higher. So that means the light that we're hitting this metal surface with must have more energy at the shorter wavelengths, or at the higher frequencies, which is what this equation basically tells us. So bigger frequency, bigger energy for our light. That's why our electrons off this metal surface get knocked off with more force or more energy. If we shine more light, that doesn't actually give more energy total being shined on the surface. It's really just, it's more, basically, since shining more light results in more electrons getting knocked off, that really means that light that we're shining really must have some kind of particle component to it. And you'll often sometimes see the term in this, like if you're reading in the text, you'll probably see a term that says quantized, which basically means that light kind of has these particle little packets of energy that we can kind of relate to. And turns out we can track and calculate the energy of those little what we call photons. So when you see this term photon, that photon really is kind of what we think of as the particle form of light. So one photon of light, we can apply this equation. A single photon of light should have an energy that's equal to this constant, Planck's constant, times the frequency of the light itself. And what we're going to end up seeing that these energies are going to be really, really small, but that's all it takes to potentially knock electrons off a metal surface. And if you remember earlier this semester talking about metals usually lose electrons relatively easily. We'll talk about some other periodic trend things with that here in the next chapter or so that'll kind of reinforce some of that a little bit as well. But metals usually lose electrons easily. That's why this kind of effect also typically works best for metal surfaces in particular. You can't just shine a light on any surface and expect electrons to get knocked off. It's not that common, but metals in particular, this effect works pretty well for. And really the most important part of this photoelectric effect is really this equation that kind of comes out of it. We'll come back to that equation in a second. Now, if we're talking more about the photoelectric effect itself, you'll sometimes see this top equation pop up where the kinetic energy of the ejected electron is equal to the energy of the incoming photon minus the electron binding energy. And this should say electron here. If you have a previous version of the slides, I did catch a typo as I was kind of putting this together where I think this might have said photon, so I do apologize for that. It should say electron right here. And what this equation really means, if I go back to this kind of image for a second on the previous slide, the energy that's coming in here of this light, this energy minus the energy that basically is holding the electrons on the surface, that difference should be the energy of the electrons that get knocked off, their kinetic energy. That's what this equation is basically saying. So the kinetic energy of the electrons that get knocked off should be equal to that energy of the incoming photons of light minus what we call this electron binding energy. You'll sometimes hear it called a threshold energy. And as we go a little bit further on into this chapter and the next, you'll sometimes hear it called an ionization energy as well for that particular substance or metal. And again, the probably most important equation out of this whole photoelectric effect is this one. This is the one that's going to come up and you'll probably use the most often. And this is the fact that energy of light is related to the frequency of the light. And again, the h in this equation, that's Planck's constant. You see that constant value here, 6.626 times 10 to the minus 34 joules times seconds. Well, this is a really tiny number, so even with really big frequencies, like the energy of a single photon is still going to be very, very small. Usually probably about 10 to the minus 19 joules is kind of the general size of energies that you're going to see for photons in the visible spectrum. All right. The other last part of this equation, oops, I apologize for that. This equation for the energy here relating it to frequency is only for a single photon. And I do want to emphasize that because you will sometimes see problems that might have multiple photons involved. Now we'll look at an example problem of that here in a moment. And if you have multiple photons, the only way you can use this equation to relate energy and frequency is if you're only looking at one photon. And so we'll kind of see that here in a second as we take a look at this example. So working an example, and again, I'm going to try kind of the whiteboard version of doing this. And again, so let me know how this way of kind of working examples works for people, if everything's kind of visible as we're going through these. But in this particular case, we want to work an example where we have a laser pulse that we're told has 4.15 times 10 to the 15th photons. And we're told that the whole pulse has an entire total energy of 2.68 millijoules. And it wants us to calculate the wavelength of the laser. So one other kind of general piece of information here. Typically when you see this term laser, you will sometimes see the word monochromatic. And I'll write that kind of out here as well. So if you see the word monochromatic, you can kind of probably sound through it to make sense of what that term means. But mono meaning one, chromatic kind of referring to color. Basically, you have a laser that has one color. Most lasers probably are monochromatic. They have a single color, meaning that all of these photons should have relatively the same wavelength. Very, very close, if not exact. So for us to find that wavelength, we're going to have to use kind of a couple of these equations that we've now seen in this chapter that deal with energy and also that deal with kind of relating wavelength and frequency, right? Because we just saw previously from the photoelectric effect slides that the energy of a single photon is equal to Planck's constant times the frequency. But what we're asked for in this case is the wavelength, right? And we saw also previously, though, that if we know the frequency, right, nu, c is a constant as well, then we can find our wavelength. And so we can use these two equations kind of back to back, or if you want, you can actually do a quick substitution, right? If you solve for the frequency here, you're going to get c over lambda, and you can substitute that in here. And so you can also write this as energy of our photon can be equal to hc over lambda. Right? That would be the other way we could write an equation for the energy of a photon. Now, the only thing is, for us to use this equation, we have to be talking about a single photon, right? But this example has lots of photons and some total energy of all of those photons. Well, if we want to be able to use this equation to find the energy, we need the energy of one photon. So all we should have to do is take the energy of all of our photons divided by the number of photons in our total laser pulse, and that should then give us the energy of a single photon. Right? So if I take our total energy here, one sec. Oops. If I take our total energy of 2.68 millijoules, which that milli prefix really means 10 to the minus 3 joules, right? That's our total energy. If I divide that by our total number of photons, 4.15 times 10 to the 15th photons, that now is going to give me my energy basically per photon. Right? And so if I divide that out, I think I have this number sitting over here in front of me. That's about 6.46 times 10 to the minus 19 joules. So this is then the energy per photon. Is the way to kind of think about that. And right, that's really, this is the value that we want for our energy for us to really be able to use this equation. Now that we have the energy for one photon, now we can come to this equation. We have an energy. H and C are both just constants, so now we can solve this for lambda. Right, so lambda, let's scroll this up just a little bit, rewriting that top equation, solving for lambda. Lambda is going to be equal to hc over the energy, where h, Planck's constant, 6.626 times 10 to the minus 34 joule seconds, times the speed of light, that's c, 3.00 times 10 to the 8th meters per second, all divided by E, our energy that we just found, 6.46 times 10 to the minus 19 joules. And then at the end of this, what we're going to get is a wavelength in units of meters. Now, one thing I will emphasize here, you will want in this chapter, more than probably any other, you will want to be really careful when using your calculators about scientific notation, right? So if you're putting things into your calculator, you're typing in 6.46 times 10 to the minus 19 down here in the denominator. If you just say all of this on top and then hit divided by 6.46 and you hit a multiplication times 10 to the minus 19, if you don't put this bottom part in parentheses, this times 10 to the minus 19 is probably going to end up on top, and you're going to be off by 38 powers of 10 on your final answer. You're going to get a final answer that the power of 10 probably isn't going to make a lot of sense. So do be really, really careful about that as you're going through examples. And so in this case, if we do this properly, again, we said wavelengths, if it's in units of meters, if it's visible range, probably somewhere like 10 to the minus 7, roughly, or if at least if it's close to the visible range. I think this value is just outside of that visible range. It's about 3.08 times 10 to the minus 7th is what I got when I calculated this. And so if we're looking at this, this is, again, units of meters. A lot of times, like this question, I didn't actually specify the units. So a lot of times you do probably want that in nanometers. So if I convert that to nanometers, that's 308 nanometers, right? And again, that's to go from meters to nanometers, like this conversion. If I wanted to show that, say times 1 nanometer over 10 to the minus 9 meters, and that would be that conversion. So 308 nanometers should be the wavelength for all of those photons in this particular laser pulse. And so this hopefully kind of is a nice example of kind of encompassing all of the pieces of a lot of the different things that we've seen so far. Right, we have our energy equation. If I scroll this up just a bit on the work that we just did, right, we're kind of combining the two main equations. These are probably the two most important equations that we see in the early part of this chapter. And by combining those two, we're able to find the energy for our the wavelength of our particular laser to have that energy. All right, if we take a look at, I think I have one more example here. Next example. So second example, this one deals with the photoelectric effect kind of specifically in terms of kind of the terminology anyway. And so we're told if we have a metal that has a threshold frequency of 5.95 times 10 to the 14th hertz, what is the maximum wavelength of a photon capable of causing an electron to be emitted from the surface of the metal? So a couple things here. First, the term threshold frequency. This is basically like the threshold frequency. That's usually the minimum frequency necessary to be able to knock an electron off of a surface, right? And it's a minimum when we're talking about the frequency, because then it asks about maximum wavelength. But remember, as wavelength gets bigger, the frequency does get smaller. So we need a frequency above this value, which means whatever wavelength corresponds to this, the wavelength can't be bigger than that wavelength, or else that energy is going to get too small and it won't knock an electron off anymore. And so that's kind of a terminology-wise here, kind of trying to describe what's going on. And so really all we need to do is take and convert this frequency into a wavelength. And that wavelength should be the maximum possible wavelength that you can have and still knock an electron off of this metal surface. Otherwise, we would need a shorter wavelength because that would have more energy. So real quick, just kind of showing this then, right? We saw in the problem above, Speed of light is equal to our wavelength times our frequency. That's kind of our general equation here. So again, looking for wavelength. So wavelength should be equal to c over the frequency. Oops, just wrote that. And so from here, just plugging in our pieces. Speed of light, 3.00 times 10 to the 8th meters per second, divided by our frequency that we're given in the problem, 5.95 times 10 to the 14th hertz. And we're going to get this, again, in units of meters, right? Because hertz, this unit really is like 1 over second, so the seconds will cancel here, and we'll just get meters out for our units. And that's going to give us about 5.04 times 10 to the minus 7 meters, which again is kind of that range we expect for something in the visible spectrum. And if we convert that to nanometers, again, that's about 504 nanometers is what that wavelength would then be. But I just wanted to kind of point out terminology more than anything other than just reviewing these equations. Threshold frequency, again, if you see that term, or you sometimes might see the term threshold energy, that's the same as that electron binding energy in that photoelectric effect equation that we saw before. All right. So I'm going to go back to kind of talking about some general things here with atomic structure. And really, those are probably the big equations that you'll see in the early part of this chapter. A lot of what we're going to kind of move into now is going to try to relate some things with light. Oops. Sorry, let's try to get our slideshow to start showing full screen again. And the rest of this chapter is really going to look at kind of relating light to things with atomic structure. In the first bit of this, we're actually going to talk about, back up, I think it's one slide too far there, something called the Bohr model of the atom. And we're going to relate this to then something called atomic line spectroscopy, which is what all of this week's lab is also going to focus on. So first, though, the Bohr model of the atom. So it's based off of the Rutherford model that we talked about earlier this semester, which, if you remember, Rutherford, in terms kind of experimentally, he did a gold foil experiment that really discovered that atoms have nuclei. So the basis of this model is that there is some positive charge that's at our nucleus. And the Bohr model kind of proposed that, well, our electrons then, they don't just kind of all float around out here, but they travel in circular orbits. And we're going to see that this model is not perfect, but there are some things from this model that give us some kind of general understanding as far as trying to explain some things that we experimentally can see. And so one of the most important ones, and kind of the reason this model of the atom really first started gaining a little bit of traction, was the fact that it was the first model that properly explained something called the atomic line spectrum of hydrogen. And so going into what that atomic line spectrum really is, if you have an atom, atoms are actually capable of absorbing and releasing light. So how that can really happen, and actually, again, I think I might actually zoom out here for a second to kind of draw this. It might be easier for me to try and draw something here than explain it with just words. And so if I'm looking at this atom, so I'm going to kind of draw a quick sketch of the Bohr model of the atom here with some kind of circular orbits. Pardon my lack of artistic skill here. I'm already artistically challenged before I have to do this on an iPad, and so it doesn't necessarily get better, unfortunately. But if I have circular orbits for all my electrons here that I'm trying to draw in, what can happen is if I have an electron that's in here at this closest orbit to the nucleus, where all of my positive charge is, what can happen is if I hit this atom with light, it's possible that this electron can actually move out to an outer orbit if our atom absorbs a photon. We call this process excitation. And so if our atom absorbs light or absorbs a photon of light, we say that this electron can potentially be excited from one of these inner orbits to an outer orbit. And these orbits, the closer you are to the nucleus, kind of the more stable that is. And so when an electron goes to a higher orbit, we'll often call it like a higher energy orbit, because it's less stable if it's at a higher energy. And so that's how atoms can absorb light. But what can happen is atoms can also actually emit light. So let's say we have an electron that's been excited and is out in one of these outer orbits over here, and then that electron actually wants to go back down to one of those inner orbits. When that happens, this can actually release a photon. And we call this process something called relaxation. Right? And so these are kind of the two ways that atoms are able to interact with light, to both either absorb it through excitation, and basically our electron goes from one of these inner circular orbits to an outer one, and then our atoms can actually then emit light through this process called relaxation, where the electron moves from one of the outer orbits back down to one of those kind of more stable inner orbits. So we're basically going from a higher energy to a lower energy, so it gives off energy in the process, and it gives off that energy as a form of light. And when we talk about this term atomic line spectra are basically these photons given off through the relaxation processes for atoms. So basically, you take an atom, you hit it with all wavelengths of light in the visible spectrum, which you just hit it with white light. That's what white light is basically a combination of all wavelengths. And so you hit it with all the wavelengths in the visible spectrum. The atom's going to absorb some of them and then basically emit some of them back out. In atomic line spectroscopy, I'm going to go back to our slides here now. Atomic line spectroscopy is going to be the image that we see, or the colors that we see of all the light that's basically released. So this is the written description of kind of the image that I was drawing out a second ago and kind of the terms. And this is then an image then visually of what we call these atomic line spectra. So atomic line spectra, they're usually mostly black with just a couple colored lines that will usually show up. And these colored lines represent energy transitions of an electron going from an outer or higher energy orbit into one of those inner orbits that's a lower energy, and it releases photons that have these specific colors, which correlate to a specific energy. Some atoms will have more lines in the visible spectrum than others. Like right here, hydrogen has 4 lines in the visible spectrum. One of the things you're going to be doing in lab is trying to figure out approximately what are these wavelengths by doing your calibration curves this week in lab. Some atoms, even though they're bigger than hydrogen and have more orbits and things for those electrons to move between, they might actually have fewer lines that show up in the visible range. Right? Sodium only has 1 that shows up in the visible range. It's in the yellow color. That's actually why if you ever see sodium get burned, sodium being burned, like if you have especially if ions like in a solution that's getting burned or something, it burns yellow. Or if you have sodium or salt, a lot of salts with sodium that happen to be like in a flame of some kind, you usually get a yellow flame from it. That's because that's the transition there that we see. It's the only one that shows up in the visible range for sodium. There's other transitions that can occur, but those energies are outside of our normal visible range. Now, the whole reason the Bohr model of the atom was so good, and kind of if going back to like our picture of our atom and this idea of circular orbits, the reason this model was kind of first accepted when it came out was that for hydrogen, that model perfectly predicted what all of these wavelengths should be for hydrogen in its spectrum. And we had never had a model that was able to do that prior. And so that was kind of what really took off with this model initially. And in fact, here's the equation that can kind of model that process or show what's going on with it. So here we can model or predict the wavelength of light that should be given off during one of those relaxation steps by taking this equation, where R here is going to be our Rydberg constant. M and N are actually just going to be our levels that our electron is relaxing to and from, respectively. So when you use this equation, M, the way I have it written here, should always be smaller than N. This will be like the smaller number, this will be the bigger number, regardless of kind of which direction you're going. Most often, this equation is going to be used to look at wavelengths of photons being emitted, but it can also be used to figure out what wavelengths can be absorbed as well. And that works for the same process. As long as you have the smaller value here for M and the bigger one for N, that won't change. You'll keep that the same regardless whether it's emission, absorption. Just you want to know which direction things are going. In the case of hydrogen in particular, all of the lines in the hydrogen series that we visually can see, it turns out that the M for all of them is 2. And then we have different N values where N can be like 3 or 4 or 5 or 6. And so the transition from like the 3 to 2 energy level, or the 4 to 2, or 5 to 2, for kind of those orbits, those all produce basically lines that we can see in the visible range. We refer to that then as the Balmer series for hydrogen. So in lab this week, all of those wavelengths for hydrogen, when you're trying to figure out at the end of the lab the transitions that are producing those wavelengths, the M in this equation should be 2 for all of them, and then you're really solving for the N values. And these numbers for these orbits that we're talking about should always be whole numbers. And we'll talk a little bit more about something called quantum numbers at the very end today, to kind of see where those things are coming from in kind of our current model of the atom. Because here, as we're about to see, there's actually some problems with this Bohr model, unfortunately. Because all of this equation works really, really well for hydrogen, but we're going to see as soon as we move away from hydrogen, it doesn't necessarily work as well. Now, before I do that, though, again, we're kind of one more general example that I want to kind of take a look at. And so this is kind of a multiple choice question, but I want to kind of write out some things here to talk about as we look at this problem. This is a really common question that tends to show up on like exams, particularly like ACS exams and things like that. I can probably guarantee you'll see something similar to this on probably a final at the end of this semester, and probably on the final, honestly, even for 12-12. It's a pretty popular question on this kind of topic, where it says, which of the following transitions for an electron relaxing will result in the emission of a photon with the smallest frequency from a hydrogen atom? So there are a number of pieces kind of word-wise in this problem, but some things to kind of keep an eye on. First off, it says relaxing and emission. Anytime you see these two involved, like if it's an emission of a photon or the process of relaxation, like we were talking about kind of before that I had sketched out, that's always going from a big N to a small n. So if some of your options are actually, like if these were reversed, like if it was like 2 to 4 or 2 to 5, you could immediately throw out those options. And that's pretty common. Like if like an ACS kind of format for this type of question, it's like, oh, which of these transitions will emit a photon with the like shortest frequency, or smallest wavelength, or whatever. Always make sure you're getting the right direction of transition. Relaxation or emission, always big N to small n. If it's an absorption, then it's small n to big N. All of these are big N to small n, so they're all relaxations of some kind. And we're looking for the transition that's going to produce a photon with the smallest frequency. So when we think about frequency, and I'm going to do this kind of from a conceptual standpoint, because if you want to, you could actually take each of these N values and actually just go back to our previous slide. 1 second here. And if you go back to our previous slide, you can actually just plug those N values into this equation where the smaller N value goes for the M, the bigger N value goes here for the N. You could actually just calculate the wavelength for each one. And then you could answer the question and basically remember that as wavelength gets bigger, frequency gets smaller, and you can answer the question that way just doing the math. But I think that takes a long time to go through, and you can actually reason through it kind of conceptually a little bit faster. And so reasoning through it kind of a little bit more conceptually, I think the best way to think about this, one thing that's going to happen with all of these energy levels as you start moving farther and farther away, if I come back to kind of my little sketch over here, each time you go up an energy level, that new energy level is getting closer and closer to the energy level before it. So basically the gaps between energy levels, as you go farther and farther out from the nucleus, those gaps get smaller and smaller and smaller. So for instance, like over here, the gap in energy between n equals 4 and 3 is a smaller energy gap than the gap between 3 and 2. Right? That's what I'm trying to kind of get at as far as the trend that we'll see. And that will always happen. Like the gap between 4 and 5 would be smaller than the gap between 4 and 3. And the gap between 5 and 6 would be smaller yet, and so on. So in this case, if we want to know what transition gives us the smallest frequency on a photon, remember what we saw before was that for energy is related to Planck's constant times frequency. So energy and frequency are directly related. If our energy gets smaller, the frequency will get smaller because this is a constant. So if we want the smallest frequency, we really want the smallest energy gap. And so if we're looking at all of these different ones to compare, like 5 to 2 is a much bigger gap than 4 to 2, right? It's got a whole extra energy level to it. 4 to 2 is bigger than 3 to 2. And so our comparison really becomes the energy gap between 3 to 2 and 4 to 3. And this is where the last part that I said a second ago comes into play. The farther out we go, the smaller your energy gap keeps getting. So the smallest energy gap is actually going to be this one, this 4 to 3 transition. And if it's the smallest energy gap, that should be the smallest frequency then as well. And that can be a conceptual way then to actually go through and look at this problem and try to figure out which of these is going to give us the smallest frequency for these different transitions. And there's probably, if you look at like some of the example problems I'm going to post for this, as well as like the homework, for kind of any of the classes you look at the homework, and probably guarantee there'll at least be 1 or 2 questions kind of similar to this, because this is a pretty popular way of asking these kinds of questions to try and really, more than anything, conceptually check to see how you're understanding things. You can just use the Rydberg equation and just do the calculations and find like what are mathematically the frequencies for all of these, but that's a lot more work, I think, than what is necessary if you can understand what's going on here and just kind of relate things conceptually as far as the general trends. And that general trends being the farther out you go, the energy gaps get smaller. And again, energy and frequency directly related, so the smallest energy gap corresponds to the smallest frequency. That's how we can get to this answer. All right. Oops, sorry, that was not where I was intending to start back up. All right, so kind of moving on from that, and again, you can kind of check for my lecture sections, like the in-class examples, as well as the homework for some more problems that are similar to that. Please feel free to email me if you have questions on that. But the other thing I kind of want to touch on here is that the Bohr model, while it's really, really great for hydrogen, it unfortunately isn't perfect, right? And so what can happen here is that if we use the Bohr model equation for pretty much any other atom, it doesn't really work. It can work if those other atoms have lost all but 1 electron, meaning if they're all just like single electron systems, which maybe for like, if you have like helium +1, like maybe that's reasonable, but it's not very reasonable for something like iron +25, right? That'd be the only way to have iron with 1 electron is as a +25 charge, which is not something we're going to be working with, so it's not reasonable for us to think about it that way. And it turns out that really as soon as you add a second electron to the atom, the Rydberg equation doesn't really work very well anymore. And really the whole Bohr model, the atom starts to break down, unfortunately. And a lot of the reason for this, in terms of like why this happens, is that it doesn't really effectively account for electron repulsions, right? All electrons have negative charge. And so putting multiple negative charges on the same atom, there are going to be some repulsions that come from that. And the net result is that those repulsions, like this model of our atom has no way to account for what effect those repulsions have. And it turns out those repulsions are going to have some impact. And there's also actually a larger impact into something called like eventually we'll talk about as orbitals. And the fact that the circular orbits aren't the best model to describe where our electrons are. We're going to see that kind of as our next piece that we're going to kind of go forward to. So realizing that the Bohr model wasn't really accurate either, even though it was good for hydrogen, we still wanted a model that works better for everything. And so kind of separately from that Bohr model of the atom, there were some other kind of things that were going on at the time, kind of in the early 1900s. And eventually we're going to work our way to the modern model of the atom from this. But the starting point was a scientist by the name of de Broglie who figured out that if particles are small enough, we can actually treat them as having wave-like character. And he kind of reasoned through this with the thought process of, well, we see light, and this is about the same time that the photoelectric effect was kind of being discovered and really first kind of understood. And the fact that light itself has wave and particle-like properties and behavior. And so scientists started thinking, well, if our particles are small enough, maybe particles can also have a wave-like character. And de Broglie was able to actually kind of model this to a large extent, even came up with an equation. We probably will not use this equation very often. Of all the equations in this chapter, it's probably the least important one. The other ones are probably more important. And one of the big things here, though, from this equation is just simply that particles can have this wave-like character. And that thought process, when scientists started thinking about it, they started thinking, well, what's the smallest particle that we really know of right now? And at that point in time, the smallest particle scientists really knew about was the electron. If you remember back to our kind of atomic structure before, like we talked about the particles of an atom, we have electrons, protons, and neutrons. electrons were by far the smallest of those particles. And so that was really kind of the next big breakthrough in our atomic structure picture, was that we wanted, instead of thinking about electrons always just being a single particle that's at one specific spot in an atom, what if we thought of electrons as waves instead? And this is really what gave birth to what we now call our quantum mechanical model of the atom. And it was developed initially by someone named Edwin Schrodinger, who came up with what we now call our Schrodinger's equations. And so on its surface, the Schrodinger equation doesn't look all that bad. We see it's basically kind of a relationship here where we take something, this H with a little kind of hat symbol on top of it. We call this something, we refer to this as the Hamiltonian operator. And basically this equation says that if we take this operator, which is a mathematical function I'll show in a second, times something called a wave function, we should get back an energy times that same wave function. And any function here, the psi, this wave function, any function that we can perform this equation and have this work, that's what we call a solution to the Schrodinger equation, which eventually now we consider atomic orbitals. And like I said, this equation looks kind of simple at first, but fortunately it's actually not that simple. There's a lot of calculus involved. And if you enjoy calculus or if you enjoy chemistry, we will probably see this equation again in some higher level classes where we'll simplify it some and break it down as far as like how we can actually use this and how practically this is applicable. For right now, we're going to kind of simplify things down. We're not going to worry about using this equation at all. But I do want to kind of point out what are some interesting kind of bits of information that we want to know and understand that come out of the Schrodinger equation. And a lot of the biggest things that are going to come from this is that Schrodinger's equations, just really their purpose, Schrodinger's equation and really the solutions to the equation, they help us describe where an atom is, where an electron is in an atom. And in terms of chemistry, that's extremely important because as we talk about chemical reactions are always all about the electrons and where the electrons are and kind of how they interact. So understanding where electrons are in the atom is paramount to really understanding how interactions between atoms or even molecules are going to occur. And so the more we understand about where electrons are and how they behave, the better we can start predicting, understanding kind of compound formation and just general reactions. So from a chemistry, just kind of application standpoint, this is why we care about being able to model this more accurately than just like the Bohr model of the atom that we saw before. And we're going to kind of work our way towards it here eventually, kind of bear with me here a little bit from the into this theory part. But our goal is thinking about like, what does all this mean? Well, what it really means is if we start thinking about the electron as a wave, instead of having one specific spot where the electron is, we can start talking about regions of space where the electrons generally are. And that's maybe a more effective way to talk about things. And this comes from something called the Heisenberg uncertainty principle, which gives rise to this whole idea of what we call atomic orbitals, which is most of what we'll focus on in our next lecture. But I'm going to give a couple details about this here to kind of wrap up this one. So the Heisenberg uncertainty principle itself, it specifically states that it's impossible to know the position and the path of an electron at the same time. And there's an equation that models this. The delta symbol here is a little bit different than what you're used to. This delta x is the uncertainty in the position, and the delta rho here is the uncertainty in something called momentum. Well, momentum is the mass times the velocity of that object. That's how you calculate momentum. And basically it says that these two uncertainties times each other has to be greater than this constant. And this is Planck's constant again showing up here. So this is a really tiny number. But to give some perspective here, if we're talking about something that's the size of an electron, the uncertainty in the position of an electron and the uncertainty with how fast that electron's moving, like it's impossible to really accurately know both at the same time. Turns out it's only like in order basically to find exactly where an electron is so that like the delta x is almost zero, that means that we have to usually hit the electron with something. And once we hit it with something, we don't know where it was going. We don't really have any information anymore about what its path was. And so we can really only ever know where the electron is, or the real thing that we can relate this momentum to, this part, we can really think about this as the energy. So we can either kind of know the energy of the electron, or we can know where the electron is exactly. And for scientists, it's actually more useful to know the energy most of the time. And this is actually what gives rise then, and it's actually easier for us to measure energy, which again is related to like the velocity of the electron. and its mass, and we know the mass of electrons relatively accurately. So if we can find the energy, and we know these two values really, really well, because again, energy is related to the velocity, that means that the position is what we don't know very well. And that's what gives rise to this idea of orbitals for atoms, instead of just these circular orbits that we were talking about before. And so I know that's a lot of kind of a stretch the first time you see a lot of this information. Don't panic too much about that just yet. I'm going to give a couple more pieces of terminology here, and then I'm going to kind of wrap up by introducing something called quantum numbers. That's what we're going to start our next lecture with, and that'll be hopefully at the start of the next lecture. We'll actually start to hit what out of all this stuff we're ending with right here, what are the important pieces? Like what are the applications of this? Because a lot of what you're seeing right here, we go into detail on all this stuff in our upper level classes. You don't need to necessarily understand every detail of all of this right now from a conceptual standpoint. But there are some basic fundamental things we'll want to take away from this that we'll start kind of describing a little bit more at the start of our next lecture. But last little bits here. So terminology-wise, these wave functions, that was that Greek letter psi that we saw in that Schrodinger equation. Those wave functions, those are solutions to that Schrodinger equation, and these psi basically represents an electron as a wave. And in particular, the most important part is that it describes a overall location, and the physical interpretation we now have for these wave functions is we refer to these as atomic orbitals. Right? So atomic orbitals, when you see that term, they are not a real physical thing that you can like take out of an atom, for instance, but they're really just a description of space, like a three-dimensional shape where this is where the electron is for that particular electron. And we can get into more details, like talking about square of wave functions being probability of where to find it. Again, for this class, this part's not very important, but that's something that does come up kind of from a theory standpoint a lot of times with this information. The biggest thing probably right now is this. When we see or you hear this term wave function, really these wave functions, they're just a mathematical function that gives us a three-dimensional shape that we think of now as atomic orbitals. That's probably the most important part to take away for right now. And what we're going to look at next time, I'm not going to go through all of these just yet. All of these wave functions or atomic orbitals can be described by a relatively simple set of numbers that we refer to as quantum numbers. And there's 4 total quantum numbers. And it turns out any first 3 quantum numbers as a set will always describe a specific atomic orbital in an atom. And then if we actually have a complete set of 4 quantum numbers, now we can actually talk about one specific electron in an atom. And that'll be kind of where we pick up with next time in the next lecture that I'll have posted. And so when we get into more with these quantum numbers, what you're going to see is basically these quantum numbers are just kind of, they're sets of numbers that are all related to one another, but they help us describe kind of physically, and really the nice thing is they relate very well to the periodic table, but they'll give rise to the different types of orbitals that are out there for atoms. So if you've had chemistry before, or if you've just heard people talk about like s orbitals or p orbitals or d orbitals, it really all comes from these quantum numbers. So quantum numbers are what we use to describe atomic orbitals and to another extent electrons as well. And so next lecture, we'll take kind of these last 4 or 5 slides and we'll spend some time focusing on like what are our main takeaways that we care about, that we can use this information for. So like I said, if you're kind of looking through some of these last few slides and I feel a little overwhelmed, it's okay. I read a little bit from the text and kind of see some of the background information, but this next part with quantum numbers that we're going to get into, and then using that to eventually relate to like orbitals and shapes and something called electron configurations, those are going to be the really important parts of this material. So don't worry too much about like memorizing like kind of specific definitions or things from the last couple slides, or kind of understanding every detail. We're going to get to kind of the main applications of this. So kind of bear with us in this process. This is kind of the stranger part of some of the concepts that we're getting into. But at the same time, we kind of need to know where does this stuff come from rather than just throwing quantum numbers at you. So that's what I'm trying to provide some perspective of where these quantum numbers are coming from, so that now as we start talking about them and using them to talk about what we call these atomic orbitals, we at least have a little bit better feel of kind of what they are. So that's all I'm going to have for this time. I will have, like I said, more of this up hopefully in the next day or two for the next lecture. That'll talk more about quantum numbers and a lot of their applications and what they mean for atomic orbitals.